So we'll just wait for our attendees to join in. We'll just wait another minute.
Oh, oh.
Okay, great. So I'll just quickly begin now.
Yeah.
While our attendees keep coming in. Welcome to the Blue Circle. It's such a big privilege and pleasure to connect with everyone and our distinguished keynote speaker, who is handpicked because of the think input and the rich experience he brings in. Thank you also to our distinguished audience for joining us, most of whom were CEOs, CXOs, and senior leaders. Many of them are members and are repeat visitors to our webinars. This is very encouraging and motivates us to provide even higher levels of dialogue through the online mode as well. For those of you who are new with us today, Blue Circle is the world's first sector-specific networking platform for industry professionals that's built in India. We currently focus on 20 sector communities such as renewable energy, e-mobility, real estate, logistics, and many more. We also present socioeconomic insights, which ultimately determine the evolving complexion of the market. Along with our weekly webinar series and our digital publication, you will be happy to know that we have recently launched the first version of the Blue Circle app for industry professionals, somewhat like the sector-specific LinkedIn, a space to have meaningful conversations, connect with over 15,000 plus like-minded leaders from India and across the globe, house high-quality curated content, and access business opportunities across these sectors. Now, without further ado, I'm pleased to introduce today's keynote speaker, Mr. Sudhir Pathak, Head Central Design and Engineering, Hero Future Energies. He is responsible for designing and engineering of grid-connected and rooftop solar projects, both domestically and internationally. Prior to Hero Future, he worked with Acme Cleantech, Tata Motors, later moving to NTPC Limited, where he was responsible for the erection, testing, and commissioning of substations and generators. Subsequently, he was transferred to NTPC's engineering department, where he undertook system studies of projects. Till date, he has successfully bid for and designed more than 5 gigawatts of solar power plants. And for today's topic, Mr. Pathak will be discussing energy transition, challenges, and opportunity. Now I request Mr. Pathak to please begin the session. Thank you.
Thanks, Gautam. Thanks for giving the brief, and I'm really delighted to be delivering my speech, or you can say, kind of a small discussion on the relevant topic. This is about the energy transition. So let me share my screen. I've made a small presentation where I will try to take all the audience to go through that. Just, yeah. Is it visible?
Yes, Mr. Pathak.
Okay, thank you. Hi all, pleasure to be here. So I will just try to start the presentation. So today we are in the world where, let me take you to the first one that will give us the insight view of that. So let me first mention about the problem statement. The problem statement as of now is that with all these recent, whatever we say as the climate change impacts, which we have all across the globe, we can see the huge heat waves coming even in the UK, and a lot of typhoons and here and there, and even droughts. So the reason the scientists have told that these all are because of human-induced warming. So whereas like if we compare with the pre-industrial era, which is somewhere taking the base somewhere between 1850 to 1900, till date we have reached 1 degree Celsius approximately above that pre-industrial era. And as per various discussions in COP, as we know that COP27 are just going on and concluded. So wherein 1.5 degrees Celsius temperature of our Mother Earth has been told to be kept in that limit. So if you see the graph, let me take it in the pointer mode. So if you see the graph, so as of now, we are here and we have already crossed 1 degree Celsius mark. And if we go with the same kind of emission and everything, so we will reach 1.5 somewhere 2040 or even slightly earlier. So that's an alarm for us. So I will now try to take you first through slight reasons and how and in what way scientifically we are trying to frame it. So I will be referring to one of the parameters that is called RCP. RCP is nothing but representative concentration path, which has been defined by IPCC. It has defined broadly, although there are more than these numbers, like when I say these are 5 categories, but actually there are more. But I've tried to put them in the important categories. When I say RCP 1.9, so what is 1.9? 1.9 is nothing but is a radiative forcing unit. Whereas there is an energy balance, there's a heat balance of in the Earth. Whatever solar light comes to the Earth, some of them is reflected right from the stratosphere, ionosphere, some passes through, and some is being absorbed on the Earth surface, and there also it is getting reflected. From that perspective, there various numbers 1.9, 2.6, 4.5 has been defined. So that it says the change in the radiative forcing, that is 1.9. So if because of greenhouse gases and all those stuff, whatever emissions we have, so if the radiative forcing means the disbalance increases up to this amount, up to 1.9, then our Earth's temperature will rise by 1.5 degrees. So COP or IPCC has set that as an aspirational target, that we should limit ourselves to RCP 1.9 scenario. In case we go to the next level, which is RCP 2.6, which tells that, okay, your temperature should not go beyond 2 degrees at the end of 2100, right? So that's the target. For that, we have to have our carbon emissions start declining right from last 2 years back, which is not so, and get it to 0 by 2100. Even methane and sulfur dioxide, all these things have to go down. But again, what I perceive as of now, the way we are moving, we are also not able to achieve even RCP 2.6. Next is RCP 4.5, where it says between 2 to 3 degrees it should remain. For that, carbon emission or carbon dioxide and its equivalent emissions should peak around 2040, then start declining. And in the same way, methane and sulfur dioxide and all those things. I believe so that the RCP 4.5 is where we are heading for, but we should try to make it RCP 2.6. And RCP 1.9, I believe we've already left it. And similar way, RCP 6.0 and RCP 8.5. So 8.5 is like if we do nothing. So we know that then where will we be heading for. So now what is going to happen in case we do not do these things and we keep it unabated? So it has impact on the climate change on broadly 3 categories. One is physical category, whereas like it will have an impact on glaciers. They will melt quickly. Snow, ice, permafrost. Rivers will start flooding, and there will be huge flooding and then huge drought. There will be erosion in the coastal area, and a lot of human life will be impacted. Second is biological, whereas ecosystem wildfires now we see in Amazon and everywhere it is now it is more frequent, even in India also. And marine life, last but not the least, is human and managed system, whereas there will be huge scarcity in water, on especially potable water. Food production will go down because of the climate change, lot of seasonality variations. Settlements, cities, everything will change, economics will change, and health and well-being, it will be jeopardized. So here just trying to show that in different geographies, in all these categories, if you just for the glimpse, you can see that whatever symbols are there. So what is going to impact in which continent? So I will not much put into it. Yeah. So now, if you see the global carbon dioxide emission as of now, so this graph is showing the cumulative one, and means not a cumulative one. Every year, how much it is rising. So in these years, we are, as a globe, we are emitting 35 gigatons of CO2 per annum, which is huge, extremely huge. And with the ever increasing energy requirement, it is also increasing. And if you take various economies, definitely China is the biggest guzzler of CO2 to the level of 12 gigatons. But we are not that far away. We are like 2.5 or something as compared to other countries. So we are the third largest emission of the CO2. I would like to try to take its perspective towards the energy sector and coming to from Indian perspective. So CO2 emissions definitely are, there are several sources of CO2 emission. What we perceive, the power sector is one of the major, because it, especially in India, because it is 90% of thermal power sectors are coal fired. You can see this, almost 30% or 40% of the CO2 emission is happening because of the power sector thermal power plants, and even gas fired power plant, which are methane or energy driven. And then comes industry, like as if you say iron and steel, they use a lot of coal for melting the furnace for the process. Even cement industries, they use a lot of fossil fuel based components for their heating applications, for process applications. Next comes transport, definitely transport, whether it is small vehicle or trucks, especially heavy duty vehicles. They're the biggest guzzlers of COx, NOx. Then building heating and buildings, their consumptions, even you can say the restaurants and all those aspects, and some part of agricultural sector, cattle feeding, and even the those stuff. So in a way, this is the proportion. Just as a glimpse here, if you see this, like as of now, IPCC told in 2018 that we have the CO2 bank balance of 580 gigatons. Okay, and if you see in the last slide, where we as a globe emit 35 gigatons every year, then we are left with only few years, up to 15 years. By the time we will reach that limit, then we have to see that what we are leaving for our future generation, and we are leaving our mother earth on ventilation, on a ventilator. So that's really a very huge problem, and we have to see how we can do this kind of dirty energy transition, from dirty to clean energy transition. Again, if I say from the total primary energy demand, if you see this graph, so almost 40% of our energy is coming from the coal, and that too for thermal plants. And then 4% is remaining for the remaining that coal for other industries. Like if you take cement industry, they use pulverized coal for clinker formation, and steel industry, they use coal for the furnaces and for steel making. And if you take oil, so it accounts for 25%, which is there, we use everywhere, pervasive, even in thermal, in transportation, and even in other process industries. In this way, it is hugely, we are using the energy distribution in this format. So we are the third largest energy consuming country. However, on per capita basis, we are very less, not because we are we are using less, because we are more. So it's just a number. And as we recover from COVID, now the trajectory is moving very speedily, hugely up. And looking into the present scenario, when because of Russia war, the energy crisis, the consumption, now even Europe is trying in a way to go to the coal to survive. So it's really a big problem. And second aspect is like we import, we almost shell out $8 billion for the import of natural gas, and we shell out almost $120 billion every year for crude oil. So almost $140 billion or $130 billion every year we are spending. So the energy independence is also needed from that perspective to make ourselves secured. Now, what's the way forward? Way forward is the only single thing is called energy transition to decarbonization, and what we say as carbon neutralism or carbon neutral. So I've tried to divide the complete process into several steps. Uh, Step one comes like that any entity or enterprise or even consumer must measure, monitor, and mitigate what is their carbon footprint. So the fundamental question is that to first find out how much is our carbon footprint, and then there are ways to monitor it and then to mitigate that. So I think, in my opinion, that's the first step towards energy transition. Step two is like that. In order to make it like this, there is again a scientific approach which has been developed. So carbon emissions are typically classified into three categories: scope 1, scope 2, and scope 3. I'll define it in the next slide, this one. So why scope 2 first is mentioned? Because scope 2 is like, for any industry, it needs energy, it needs power. So predominantly they take power from the grid. So whatever emissions from purchase electricity for own use is there, that is called scope 2. Okay. So like if we are taking power from a thermal power plant, so the kind of emission that thermal power plant is making, that is called scope 2, which is called indirect sources. Then comes scope 1, which is the direct sources. Whatever at the site kind of energy which we are using, which is leading to the emission of, like we have a captive plants within that, even our own trucks and vehicles which are moving around, which are directly required for our processes, their emissions come in scope 1. And last but not the least is scope 3. Like whatever upstream and downstream, like even your sub vendors, what are they doing? Your employees, they are going for some business travels. So that also that comes, whatever emission they are making, that is accounted for scope 3. So what we need to do, we need to first monitor scope 2, 1, and 3. Then first of all measure it, then only we can monitor, and then we can start mitigating it. So coming to step 3. Step 3 is like, as we are doing as Hero Future Energies to various tier 1 clients, that we are trying to create their RE100 roadmap. You can see RE100. It simply means that whatever electrical energy they are utilizing in their system, in what way we can make them 100% RE, right? So, and that comes as uh, scope 2. Now I'll try to explain. Typically, as per our experience, we see that reaching up to RE40 is quite a simple task, where you need to have solar and wind maybe behind the meter. No, wind definitely can't come behind the meter, but wind uh, from uh, from offsite, and solar behind the meter as well as through open access. With these combo, we can easily make RE40. Then there are some banking facilities which are available in states, intra-state, as well as there's an exchange market where you can reach to RE70 with all your best efforts. But this last mile connectivity, because of the intermittency of all this stuff, you need to have storage to make RTC. To make it RTC or round the clock kind of requirement, then you need to put battery storage or pumped storage or whatever storage, even through green hydrogen storage, you can do. From that perspective, you can reach there. In scope 1 and 2, what typically industry says is path to net zero, or when we say 100% decarbonization. So there is no net emission of carbon dioxide and its equivalent. Now coming to challenges in the energy transition. So I think this is a famous, or I can say infamous duck curve, which is now prevalent all across the globe. Typically, if you see any kind of load curve, any day is like this. However, so there you can see typically two peaks are there, right? But because of the penetration of RE, especially solar gets peak in the mid of the day, which compensate for the day peak. But what happens because of that? This offset leads to this duck. The problem with this duck is that this duck is hugely problem creating, unlike the actual ducks. What happens that these loads are need to be borne by our conventional sources, thermal plants, gas plants, or to an extent hydro plants. Yeah, some more uh, wind plants are also there, but they are also uncontrolled, intermittent. So if you see the ramp rate, the way thermal plants or you can say base load stations have to ramp down and ramp up and then again ramp down. So that creates several issues, which I'll take it in the further slides. So in a way, it creates net demand curve erratic. Now, what is happening in this? I've just taken these numbers from the Power Ministry website and try to do some of my own analysis here. So what is happening here? If you see this, this particular table, so just try to see that this energy, this is the peak, this is the power, and this is the demand, and this is the availability, and whatever surplus is there, typically in the grid. So it is all the overall Indian grid. The same way, peak demand and what is peak met through various sources and what is the deficit. If you see from here to even till date, kind of, or I will try to focus because it's not yet this is yeah completed. If you see this, the energy deficiency in this year was 10% and peak power deficiency was 12%. But as the power sector grows and with RE also, you can see that now the deficiency has gone down to only 0.4%, right? That means now deficiency is now no there is absolutely not there. Whatever energy demand is there is being supplied. The same thing with the peak. But the problem statement is here. If you see this, this is the PLF of the base load stations. And since I'm an XNTPC, so when I used to be there, even at site, we used to have this ambition to run our plants at even more than 100% of PLF. But now, if you see this is the average annual average, how it has gone down to 58 or even 53%, right? That means the way the plants are been running, they are leading to high inefficiency of resources, and definitely it is making the grid fragile also, because such ramping up, ramping down is making the problem bigger and bigger. It is now evident all over. Now, if you see this, today the installed capacity is 100% if you say water 4 and 5 gigawatt. So solar and wind capacity wise is 25%. And if you see energy wise, they're 13%. If we take it 2030 targets, so 25% becomes 51 and this becomes 35. So if you go back to the earlier graph, which I was showing, that means you can, or even the PLFs of the thermal plants and the duck curve, that is going to be much more, duck is going to be much more thinner and its neck is going to be much more longer. So what is happening? We are using inefficient resources. We are dwindling, have a dwindling grid inertia. This is very important point, extremely important point. Why? Because thermal power plants, they are the prime movers. They have the mechanical devices which is running. Whenever there's a fault in the grid, their inertia, we all know I omega square. So their inertia uh, still feeds the fault and tries to make the grid stable by having a better dynamic stability and steady state stability and transient stability. However, with more penetration of RE, inertia is getting down and fault resilience is also going down. So we have a vulnerable grid as of now. Steady state, transient, and dynamic stability is definitely an issue. It is evident in highly, you can say, RE rich states like Rajasthan, where load is minimal because industries are very less, but source of RE is huge. So there have been several incidents up and down, which is leading to some kind of catastrophic failures, which in my like younger days we used to see before ABT regime came. That there was used to be several grid failures. So there is a need for change in the grid chemistry as a way forward. That is the take my take as far as to solve this challenge. Now you can see this the duct is swelling once we have a storage also. So one of the storage is one of the solutions, wherein by putting the battery storage or pump storage or even green hydrogen based storage, because now we can't stop RE from moving on because of the climate issues. There's no looking back, but every problem has a solution. Once we have a battery storage or any kind of storage, we can make this duct bottom slightly up, and this we can slightly make it sharpen like this, or not sharp but flatten like this. So our net curve will be somewhere like this. So now the ramping issues will get mitigated, and you will see that the use of resources will become more efficient. Second thing which the problem comes as a challenge is regarding the reactive power. If you see like this is the curve which I've tried to show for a synchronous generator. I was earlier all in NTPC, used to work in generating stations as well, and also in designing. So I have even by my hand maintained the excitation system and generator. So you can see, I can feel, I can sense how quick they are to respond to any kind of grid vagaries, right? So and their reactive power capability is extremely good. Yeah, for wind turbine generators and for solar power inverters, their capability curve is also wonderful. It is, you can say, at par matching with the thermal power plants. But the problem is next one. The problem here is that although our inverters and WTGs are having good capabilities of reactive power, and reactive power is responsible for the voltage regulation of the grid. What is happening? Because what we typically say RE as a DG or distributed generation, unlike thermal power plants where a big 600 megawatt of generator is just behind the GT and then it is connected to the grid. Here, or 600 megawatt is you have long lines or long cables, and then you have inverters. So that reactive power at the point of connection, that becomes very poor, because a lot of cables, or you can say a lot of transformers, cables are inductive as well as capacitive. Transformers are purely inductive from a reactive power perspective. So even though the capabilities are being governed by all these WTGs and inverters, but at the POC point, they're not able to meet the V curve in case they're running on their own. You can see that this is the deviation. This is the gap. It's a now very well-known curve to the people in this industry. So this is the problem where, and second thing, there's the time to respond. And third thing, that being of distributed nature, it is the voltage which is measured by the WTGs and the inverters is not that of the grid. So the response in the voltage control mode is very, very tough as of now. So a paradigm shift is required to be done. Second thing, typically RE is fundamentally, you can say, a very high impedance system, unlike thermal, where you used to have subtransient reactance and all those reactances during fault conditions, which leads to the fault current 3 times, 4 times more. Whereas in case of RE, the fault current is only 1.2 times more, and that too only for a fraction of a second. So that's why their fault resilience is not there. Although LVRT and HVRT curves are there, but we need to have the more adoption of the high technology to adopt this. So like RE plant act as a source of active power, but they are importers of reactive power. So during the peak generation, if you don't want to do anything, they will import reactive power, which is against the grid you can say, regulation part. There are no measures in voltage self-regulation as of now. The pre-fault conditions for in RE rich area remains hugely fragile, as I already explained, because as we keep on importing reactive power, so pre-fault conditions, because during fault we need to pump a lot of reactive power in the system to clear it and also to bring it back to the normal condition. So that leads to a lot of dynamic and transient stability issues. So STATCON and SPC deployment in the grid is imperative for the grid resilience. So this is what is now hugely debated, and now it is being resolved that now even now our grid operator, Power Grid, they are putting up a lot of STATCOMs and SPC. Comes next point as a step 4. Now regarding a scope 1 and 2 path to decarbonization. Like typically when I deal with into this part, so we are displacing all scope 2 by RE, but there are many things which you can't displace by only electricity. Like we use a lot of hydrogen as a gray hydrogen, which is generated through SMR, steam methane reforming, which takes input as natural gas or at times coal also. And that converts into hydrogen, then maybe for refinery, for desulfurization, even in many chemical applications, a lot of hydrogen is being used for glass and for other industry. So there, that is a huge emitter of CO2 and other gases. So we can have feedstock replacement of gray with green hydrogen. What is green hydrogen? Since time is short, so I will take slightly quickly on this part. That gray to green is basically like when we say green hydrogen, that means you need RE as an input to an electrolyzer. You provide water H2O to this, which will generate H2 and O2. You capture H2, and that is called green hydrogen. It has a lot of colors: green, purple, gray, brown, turquoise, and depending on the source of energy, and even blue. Fuel replacement is the second. Wherever you are using coal or natural gas for heating or LPG, you can replace that with green hydrogen or methanol or even ammonia. Third thing is CCUS, is carbon capture and usage and storage, or even somebody say underground storage. So if you are whatever CO2 you emit from any plant, if you are able to capture it and use it for some other application, like CO2 is needed for manufacturing of methanol. So this can be captured with green hydrogen. It can be producing green methanols. And mobility, where we can, a lot of work is going on, and even in Europe is now becoming slightly common to use mobility, first of all, on electric vehicle. There is already now in India is now moving on very fast, and that too also on hydrogen, either through compressed gas of hydrogen or liquefaction. So this hydrogen can make mobility either through dual fuel as of now. You can inject hydrogen, even the same engine, fuel cell based vehicle, or even IC engine is also under an advanced stage of commercialization. And then DRI is called direct reduction of iron, where we can use green hydrogen in place of coke or coal as reducer, and definitely green ammonia, which is touted to be one of the you can say a boon, wherein you can transport hydrogen as ammonia, or even use it in the fertilizer, or there are even you can use it as directly as a fuel for ships and for aviation. This is my last slide, last two slides. So definitely, as I try to give an example, that feedstock, chemical, glasses, refinery, fertilizer, steel, and even for methane, this can be used. For natural gas blending, we are working a lot into this, wherein by heating application, furnace applications, automotive, cement, beverages, and even heating application and steel. Regarding coal blending, so similar applications wherever we are using coal directly, like in cement, thermal plants, and in steel, and definitely in mobility. So we as Hero Future Energies, we are working on all of these parts and providing the solution for converting it into green, or even to, you can say, even in any form, whether in mobility form, in all the spaces. We have all the strategic partners with us, wherein we can provide all the solution. Yeah, and now a slight challenge is that today, definitely there is a challenges of having the cost of replacement. The LCOH, or what we say as levelized cost of hydrogen, it is, as of now, it is not matching with whatever we have as a present fuel. But as we move to the journey of solar, wherein we started from 18 rupees now to 2 rupees, we need to start somewhere. So there is one LCO generation and there is one as LCO delivered. Both are, as of now, that's a challenge, because there is, if you go without any kind of subsidy or any kind of support, so that becomes, as of now, costlier. So we need to have a demand creation mandate from government, which we believe is in process. Also, there is a huge need of water. So, just as sense of 700 gigaliters of water per annum you need by 2050 to reach the India emissions. And definitely safety parameters, because now for transportation you need 700 bar or cryogenic liquefaction of minus 250 degrees Celsius. So that infra is a challenge. And center state policy consistency, like about banking and all those, it needs to be consistent so that we can have a proper model, techno-financial model, which we can sustain. And definitely this quantum of water we can't get from potable water. We need to have lots of innovation in desalination. Safety norms, as I already told, and definitely financing is not there, and financing is coming up slightly. Finances are getting slightly educated in this sector. So last is that, as I was telling, that a solar story came from rocket, where there was a solar panel used to be there in the rocket. When it came down to the earth, it became cheaper, and now the tariff became sub 2. Same way, you have hydrogen, which fires the rocket. I believe that when it comes to the ground, it will also be having the same story as of this. And we as Hero Future Energies, we are here to provide the solution all across, in all the, even if you take regarding the open access, and for rooftop solar, for wind and solar, anything for RTC round the clock, energy storage, trading, and even through exchange, energy efficiency wherever you have, and green hydrogen attributes, net zero roadmap, and all these things. Thank you.
Thank you, Mr. Pathak. We'll just quickly move on to the questions now which we've received.
Yeah.
So the first question comes from Radhika.
Can you let me how to unshare? Let me try to unshare first so that I can. I'm slightly struggling to unshare. Is it possible for you to unshare from your end?
Sure, I can do that. Done.
Oh, thank you. Thanks.
So we'll quickly jump on to the questions. The first one coming from Radhika: how can cost reduction of green hydrogen technologies be accelerated?
Yeah, definitely. As I mentioned in my slide, the cost of green hydrogen. See, typically, if you see, typically 70% of the cost is of RE part, and 30% is the cost of the remaining components. So as we see the RE trajectory, it is going down, not that down, but the huge scope is there in the 30% bit, wherein the cost of electrolyzer is consistently going down with the massive scale of deployment, lot of R&D into it, and there are few noble metals within the electrolyzer which are in the research getting replaced with the cheaper. So from that perspective, and second thing, once we get a support from government, like not only financial but as a policy, like banking charges, so that will, once the deployment is larger, so definitely it will become a volume game, which will lead to cheap financing, and then bankability, and then will lead to the reduction of the LCOH. Yeah.
Thank you so much. I'll move on to the next question quickly. Prabha saying a few countries like Uganda, Somalia, Congo have gone over 90% renewable in energy consumption. Can India achieve this in years to come?
Yeah, see, so when we say 90% renewable, So there are two, three things. Like if I take an example of UK, okay, because which is slightly or much way ahead on the RE deployment. So RE has an inherent issue of intermittency. So we also, and we have a very, you can say the biggest network of grid in the world, and it is very sensitive to for any kind of demand supply unbalance or the voltage unbalance. So RE can move quickly up, but without storage it is not possible. Like in UK they have a lot of schemes where they can deploy, and there is huge deployment of storage, which will leading to a kind of grid resilience. And storage is not simple like just shaving it for frequency response, okay, for demand shaping. There are a lot of innovative in the RE, I can say in the exchange, in the, I can say, incentives like TOD metering. If you say, there should be a lot of differentiator, like the peak power, like if you take in the evening 6 to 9, that's a peak demand time. So there should be huge tariff for peak demand, if somebody wants to use that, and a lot of discounted tariff during the normal. If such gaps are there, that will help the deployment of storage, which will make a business case. So as of now, what is happening? The storage is not making that business case in India, but it is making sense in US, in UK market. So from that perspective, it is very important that we can accelerate once we have these innovations also in place.
Thank you so much. I'll move on to the next question, and then we have one more after that. The question is, can an increasingly renewable electricity system deliver the same standard of reliability, resilience, and flexibility that the current grid does?
Yeah, so I think in my presentation, I took that point in very larger detail. So I think maybe if this that question was posted earlier, so it might have been resolved by now. But definitely RE. So again, briefly, two, three things. Inertia is the biggest issue because you need a lot of inertia in the grid to be fault resilient and to quickly come back to the steady state stability. With RE, now there are issues called thermal or you can say synthetic inertia, which is being developed in the inverters, and with the storage coming into it, that also bring a lot of inertia and also the reactive power compensation. I think these things are the natural outcomes which we believe that it will automatically make it stable. Just to give an example, if you see Australia, so Australia is famous for a very fragile grid because their load centers are quite far off, source is somewhere else, and they have a lot of microgrids. Their storage is is making the big role. So I think definitely because RE is the need, storage will definitely come and solve it.
Understood, understood. Thank you. And also for sharing that example of Australia, which I completely agree with. Moving on to the last question. So far, India has installed around 7 gigawatts of panels on rooftops, falling far short of its target of 40 gigawatts by this year. How can this be corrected?
Yeah, see, now it is basically like it is not a technology issue. It is basically a policy issue. And the policy issue, why? Because unlike you can see utility scale or open access RE, wherein you are willing the power and selling it through Discom, or Discom has some kind of share into it. So in a way, in a rooftop segment, by putting the modules on the industrial hubs, you are basically snatching the rich customers from Discom, which I totally sympathize with them, because then they will be left only with the farmers to get the money, or maybe not so good, you can say, paymasters. So that is a problem. But I think the solution is there, because the Discom has to find out those innovative measures wherein like all those rooftop segments, wherever we are putting the roof, they can levy some additional charges. Not I'm saying about that ADSS and all. So there need to be hugely an innovative thoughts has to go in the rooftop segment, wherein Discom can play as a role of facilitator, and they can charge, maybe they can levy some charge for the grid offtake. And like if I say a virtual power plant, that will come, or there are a lot of innovative technology from where even if we're sourcing or sending power to the grid from the rooftop, and we are getting kind of good revenue from the off-takers, then that can also in slightly way solve it. But definitely that is not so easy, because definitely we are, or those who are become prosumers, they are taking the pie out of. So from that perspective, I think open access is much more a better solution and much more reliable as we go ahead with more of RE.
Great. I'd be eager to watch how this innovative business model comes across.
Yeah.
So yeah. But great. Thank you so much, Mr. Pathak. What an insightful and engaging session, and a privilege to hear you. And also thank you to our leaders in the audience for joining us and for staying till the end, and for always sharing excellent questions.
Okay. Thank you. Thanks.
Thank you so much.
Thanks. Bye.
Bye.